My name is Zongzhang. The title of my presentation is Please Family Search for POMDPs with Large Observation Spaces. In the presentation, I will introduce a novel approach called family search. This work is co-finished with David, Zhan, Zhang, and Aijun. I'm now a faculty at Zhang University. This is the outline of my presentation. Let's first see POMDP applications. As we know, POMDP is a famous mathematical model in the AI community. Many robotic planning problems can be modeled as POMDP problems. Here are some recent applications. The first application is motion planning or navigation. Researchers at the NUS treat intention-aware motion planning as planning and uncertainty and model it as a POMDP. Tasks such as the spoken dialogue system, visual processing management, home care service, and grasping can also be viewed as instances of sequential decision-making in the partially observable environments, and especially as POMDP tasks. A POMDP can be defined as a tuple where S, A, and Z are the state, action, and observation spaces. T, omega, and R are the state transition, observation, and the immediate reward functions, respectively. POMDP can describe two kinds of uncertainty. That is uncertainty in action effects and uncertainty in state observability. Due to the uncertainty in state observability, the agent in a POMDP task cannot fully observe its current state. So the agent needs to store belief state, which is a discrete probability distribution over the state space. All possible beliefs reachable from the initial belief, B0, and the arbitrary policies comprise a belief tree rooted at the initial belief. In a POMDP environment, an agent needs to have a policy pi, which is a mapping from the belief set to the action set. The goal of solving a POMDP is to find an optimal policy that maximizes the average discounted return. The optimal value function V star is the value function of the optimal policy. The figure in this slide is an example value function, which satisfies the piecewise linear and convex property. POMDP solvers usually need to construct the lower and upper bounds of the optimal value function to find an optimal solution. The lower bound is initialized by the blind policy and represented as a vector set. The upper bound is initialized by the FIB method and represented as a belief value pair, also known as the sawtooth representation. The interval between lower and upper bounds at specific belief B is called the gap between bounds at B. The lower and upper bounds are uniformly improvable after initialization, which can guarantee that looks-ahead policy performance is at least as good as the lower bound. So after initialization, each belief in a belief tree has a gap. The process of solving a POMDP approximately is to close the gap between the bounds at the initial belief. The process repeatedly executes two stages. The belief selection stage is used to sample a set of promising beliefs in the belief tree. The backup stage is to perform backups on sampled beliefs in some order. Let's see the backup operation first. It improves the lower bound by adding a vector and the upper bound by adding a belief value pair. Such an operation can bring the lower and upper bounds over the whole belief space, especially the space around the belief B, closer to the optimal value function. The backup operation is common in different point-based methods, but the belief selection is not. So belief selection is a key component to distinguish different methods. This slide lists some of the typical point-based algorithms and the belief selection strategies in them. Note that the algorithms labeled with red color are trail-based value iteration algorithms. These algorithms sample beliefs along a trajectory started from the initial belief in the forward exploration phase. Then they perform backup operations on sampled beliefs in reverse or around order. Such a trail-based search strategy has its strengths. The algorithms based on it are anytime and can guarantee to find the near optimal solutions given enough time. The reason behind it is that such a strategy can propagate the boundary improvements of beliefs in deep levels to the initial belief. However, its weakness is that the propagation is time-consuming, caused by the fact that it forwards search only one outcome at each belief. Let's see this figure. Students that enter the children enter the beliefs of a belief at the level d-1 need to perform backups to propagate the boundary improvements to the initial belief. The trail-based algorithms need to perform n times d+1 backups to complete this, as each trail needs to perform d+1 backups. To overcome the weakness in the trail-based search, we proposed a new method called palm leaf search, or PLEAS. Its key idea is to allow the selection of more than one outcome when the potential impacts are close to the highest one. Such a new strategy can save considerable time to propagate the boundary improvements of beliefs in deep levels of the search tree to the root belief because of fewer point-based value backups. We use this figure to expand the intuition behind it. Palm leaf search only needs to perform n plus d backups to propagate back the boundary improvements of n different beliefs at the level d to the root belief. It suggests that palm leaf search is better when tackling POMDPs with large observation spaces that needs to search deeply to find near optimal solutions. Now let's see the PLEAS algorithm as shown in this slide. Compared with the original trail-based search algorithms, PLEAS adds a for loop in lines 6 to 10. This loop allows the algorithm to search forward more than one outcome in its forward exploration phase when the potential impacts are close to the highest one. Note that zeta of b, theta in red color is the heuristic threshold function to control the palm leaf search at beliefs online. We use the heuristic threshold function zeta to select promising beliefs. Zeta is a function of b and theta, labeled in red color. This threshold function is an important part of our method. We now explain the intuition behind it. Theta ranges from 0 to 1. The distance from b to p star is greater than 1. Given theta, the larger the distance from b to p star, the higher the value of zeta, and vice versa. So this function makes PLEAS prefers to do palm leaf search in promising beliefs with deep levels only if the distance to the from b to p star is small. The current best path p star is the path generated by subset action and observation selection strategies. And the distance from B to P star is defined as the number of beliefs that B needs to go through to arrive in P star. Then, what is the optimal value of theta for the best performance? Frankly, it is unknown. But we know that it depends on model parameters and probably changes over time. So in our PLEAS algorithm, we adjust the theta automatically to make the actual ratio of POMDPs to POMD goes to C+1. Here, POMDPs is the total number of backups in the PLEAS approach. And the POMD is the total number of backups on the paths selected by subset action and observation selection strategies. C is an input constant to exploit the prior knowledge of model parameters. Now, let's see, please, the empirical results on POMDPs with large observation spaces. The first problem we use is the tag 55 problem. The problem has 56 observations. In the environment, a mobile robot moves in a 55-grid map with the goal of tackling an opponent that intentionally moves away. We use the problem to study the effects of varying the turning parameter C and the heuristic function zeta. As shown in the left figure, place with C equals to 1 is less efficient than the corresponding ones with higher values of C. It suggests that C equals to 1 is still too small to result in significant time saving. When setting C to be a value bigger than 4, place appears not to be as good as place with C equals to 4. It implies that it becomes more difficult to select promising beliefs for very deep levels of the search tree as theta decreases. The right figure shows the empirical results of two other heuristic ways of defining zeta. They are less efficient in terms of the evolution of the gaps between bounds at the initial belief. The second example is the two-robot tag problem. This problem has 625 observations. In the task, the two robots and the attack gate operate in a 7x5 grid environment. We use the larger robotic task to further study the effects of varying the input constant C. As shown in this figure, setting C equals to 10 is better than setting C equals to 4 on the larger problem. It implies that more aggressive palm leaf search is capable to get better performance on problems with larger observation space sizes. We use C equals to m times log Z in spite that, by the fact that C should be larger when Z increases, as a simple formula to set the input constant automatically. Well, here, m equals to 3.22 is fitted by using the least squares method. This slide shows the configurations of other POMDP problems with medium or large observation spaces that we will use as benchmark problems. And the table in this slide shows the performance comparison of Please and SASUP on the 6 benchmark problems. On most of these problems, this table shows that Please is substantially faster than SASUP by orders of magnitude. Now let's study Please the performance if applied to problems with small observation spaces. We use the log sample domain as an example. It is a classical domain with extremely small observation size. The left figure shows the results on log sample 78. Please with C equals to 1 appears to be better than SASUP, while after 1,500 seconds in terms of the gap between bounds at the initial belief. As C increases, Please the performance becomes slightly worse. However, performance degradation is limited as C increases. It suggests that Please is robust for problems with extremely small observation spaces. For more data, we have the following insights. The performance of HSVI2 on our test problems is worse than SASUP in most cases. And the gap mean variants are not efficient in tackling large problems. The table in this slide compares HSVI2 and SASUP on the 3 mentioned problems. HSVI2's performance is slightly better on tag 55, but much worse on the 2-robot tag and the home care problems. Gap mean variance failed to load the 3 problems in 10,000 seconds. There are some existing works that focus on developing efficient planning algorithms for POMDPs with large observation spaces. We did not compare Please with them because the implementation and experimental results on our test problems are not available for us yet. Compared with the SASUP, Please needs much fewer alpha vectors to get the same gaps on test problems, for example, the home care problem as shown in this table. This data provide a good clue to explain Please the efficiency. To achieve the same gap, Please sometimes also need to expand beliefs with similar numbers. But it needs fewer backups in finishing this. Since one backup generates an alpha vector, more alpha vectors are generated in startup. This results in additional time cost in startup's pruning process. When the gaps between bounds at the initial belief are the same, the average discounted returns of startup and place the current policies appears to be similar with each other, as shown in the table. This implies that relatively fewer vectors as lower bound in place do not sacrifice its policy quality. In our work, we also proposed a variant of place called the place-z. In place-z, C+1 is no longer the ideal ratio of pound place to pound startup. Compared with the place-z is less intuitive, but has a relatively tighter convergence bound. Empirically, place-z has slightly better results. Essentially, POMDP search can be viewed as a kind of complete best-first bin search in POMDPs. Theoretically, place the conservative bound of finding an epsilon optimal policy is not worse than the original trail-based algorithm. Finally, let's sum up my presentation. We present a novel approach called place, which allows the selection of more than one outcome when the potential impacts are close to the highest one. Please use the heuristic threshold function to find promising beliefs in deep levels during the POMDP search process. Our extensive experiments show that place is faster than startup by orders of magnitude on challenging problems with large observation spaces and robust for problems with extremely small observation spaces. In the future, we could like to use more heuristic information of beliefs in defining the threshold function zeta, define a better function for choosing scene automatically, and consider how to combine the POMDP search idea with online algorithms. Thank you. Any questions? This one? Discounted reward. The results?
So you're focusing on gap minimization.
Yes.
And I'm asking whether the actual policies that you get
Yeah.
from the lower bound are better than the ones that you get from the startup or AAAI or whatnot.
We did experiments to show that when the gaps between the lower and upper bound are the same, the average discounted return are similar with each other.
Yeah, I want to ask the other question.
Yeah.
Is lowering the gap actually corresponds to the policy?
I'm not sure. We can do more experiments to check whether it is true.
One more question? I have a question. So, so you increased efficiency for large observation spaces.
Yes.
What can you say about large state spaces or large action spaces?
It can also work on a larger state space size or a larger action space size, but I cannot guarantee that it will be more efficient than startup if the observation size is very small. Yeah.
Okay. Thank you again.
Thank you.